And on to the final video of Digital Learning Week 1. We're going to talk about the most interesting kinds of area problems now. Really start building into them for next week. And those are area problems dealing with regular polygons. Now, we've worked with regular polygons in the sense of triangles, but we haven't worked with regular polygons much larger than that. We've talked about squares, but what about pentagons, hexagons, heptagons, octagons, nonagons? What about those? How would we find the area of those things? Well, you're going to see today what I alluded to in the first lesson, which is that all of these regular polygons, their areas are actually going to be related to that of a triangle. And so our fluency with our tools for solving triangles, our special right rules and our trig, are going to be absolutely essential here. Now, as a quick reminder, that area, if someone says, what is area? Remember, this is the two-dimensional space that's enclosed by a figure. So if somebody asks you what is area, just say, hey, it's all that stuff that's enclosed within some figure, within some boundaries. And in general, area is calculated by finding some base and some perpendicular height. Great. Now, we alluded to regular polygons, but a reminder of what those are, since it's been a while since we talked about polygons. Remember, a regular polygon is a multi-sided, closed figure. That's actually what a polygon is a multi-sided closed figure that is both, and now we need to add in what it means to be regular. To be regular means that you're equilateral, all the sides the same, and you're equiangular. Now, what's fascinating here is that as we investigate regular polygons, they have a bit of an interesting way that we find their area. And the reason for this is because a polygon is kind of a mixture between a triangle and or being able to break things into triangles and a circle. Because, and you'll see from this image here, polygons are similar in notion to circles, and that they both are described in terms of a center. All regular polygons have a center just like a circle, because a center is the point equidistant, equal distance from the vertices, from the corners. In other words, this center is equal distance from all, in this case, 6 of these corners. That's what a center is. And just like a circle, we can actually describe the distance from the center to any one of those vertices on the edges. And that is actually what we call a radius, which is the exact same thing we refer to in a circle. This is the distance from center to vertex. Now, the thing that's different about a polygon compared to a circle is that a polygon does not have constant distance from the center. With a circle, this arc ensures that any time my pen is on the edge of the circle, it's the same distance from the center, because that arc is accounting for that change as I move around. However, with a polygon, you'll notice there's some spots that are closer than others to the center. In particular, the point which is directly above the center or below the center, that is perpendicular, in fact, where that line meets the center, that is the shortest distance in a polygon. And there actually is a special name for that distance, right? The radius is the longest distance to get to the edge because it goes to the furthest corners. But the distance from the center to the edge that's the shortest is called the apothem. It sounds kind of like you're saying possum with a lisp. The apothem. This is the distance from the center to the side of the polygon. Cool. Now, where is this helpful? Well, we're going to see a little bit tomorrow where we can find area of a regular polygon by breaking it into triangles. And you can kind of see that up here. When we draw in the radiuses, all the radii, it actually breaks the polygon into a bunch of triangles. You'll see here as I highlight these that our 6 radii in our hexagon break it into 6 triangles. And you'll see tomorrow, next week, I suppose, would be the time you would see this, that actually, if we find the area of any one of these triangles, we can multiply by however many there are to find the area in general. Now, the only challenge to this is how we deal with finding the area of any one of these triangles. And what we often do is we investigate what the angles are at the center of all these. So what you'll notice is, I'll go ahead and do my best to draw in all these radii. Thankfully, I have this tool to make things straight. And then we might be curious, what angles do these triangles have then? Well, the way we're going to find it is actually very, very nice, because if we want to know the angle at the top of a triangle, all we need to know is how many degrees there are all the way around, which of course is always 360, divided by however many triangles we've created, which is actually also the same as the number of sides. In other words, in a 1, 2, 3, 4, 5, 6-sided regular polygon, a hexagon, each of those angles will just so happen to be 60 degrees apiece. Now, this will be handy when we talk about next week drawing in an apothem and splitting things possibly into special right triangles, in this case 30, 60, 90, which will allow us to find the area of one of the triangles and then find the area of the whole figure. Now, let's say you want to have a formula to work with that allows you to find the area of a regular polygon without finding the area of a triangle and then multiplying a bunch. There is a formula for the area of a polygon, and it's actually written like this: 1/2 the apothem times the perimeter. And this actually is directly related to the idea of drawing in these triangles. So I'll try to see if I can illustrate that with this pentagon. But you'll notice as I draw in this pentagon, what they're doing basically when they describe this formula is they're finding this apothem here, this height, in this case, from the center to the edge. And after they find that apothem, they're multiplying basically by the length of all the sides, as if they were to stretch all these triangles and flatten them into kind of a spike strip. And that allows them to find the area of the whole pentagon all at once. Now, just like I alluded to above, you'll see next week that most generally I am not a huge fan of this formula, primarily because I think it's just more to memorize. I personally don't mind finding the area of my triangle and then just multiplying by however many I have, because again, then I only need one formula to work with, which is the area of a triangle. But you're welcome to memorize this one as well. Now, I'm going to skip this example here since it's not super exciting, but I will talk about this one in the visual of what's happening so we can see an area problem involving a polygon. So again, I might draw in here, or do my best to draw in an octagon, which no promises on what this ends up looking like. Again, we need 8 sides. Thank goodness for straight line cheats. There we go, there's our 8 sides. Then we're told that each side here is 18 feet. All the way around. And we're asked to find the area of this particular octagon. given that we also know the apothem. Now, again, I'm going to go ahead and break this up, if I can, into triangles, because again, I like to think of all these area problems with polygons as just problems with finding the area of triangles, because triangles are so much easier to find the area of. Now, you'll notice I'm not doing a perfect job of splitting this up, but I did my best. In theory, all 8 of these triangles would be exactly the same size. So, what else do I know? Again, as mentioned, we know the apothem. We know that this distance right here is going to be 21.7 units. Well, great. Why is that helpful? Because notice, if you look here, you'll see that we know both a base and a height of this triangle. So we can find the area of that triangle. The area of that triangle is 1/2 base of 18 times height of 21.7. Whatever that answer is, that is the area of one of those triangles. And I know that because it's an octagon, it's going to have 8 sides. So I'm going to take this answer times 8 to get the total area. And I'm done. I don't have to do any further work. So again, I personally like this idea. Break it into triangles, find the area of one triangle, and multiply by however many there are. Cool. Now, this small aside here is to talk about the idea that the area of a circle and the area of a polygon do become related. Because you'll notice that with a circle has a radius, and the apothem is basically the exact same height. Well, this happens because as we start increasing the number of sides of our polygon, the length of each side gets smaller and smaller. So with 3 sides, each of the sides is fairly long. But eventually we get to these very small sides in our figure. And after we've gotten to very small sides in our figure, now we are able to realize that eventually the sides will get so small that it will become a curve, which means that it's a circle. This is why the formulas for the area of a circle and of a polygon are connected, because you'll notice the apothem over time gets closer and closer in size to being the exact same size as the radius. And the perimeter of that figure gets closer and closer in size to being the exact distance of a curved circle. So the area of a circle really comes exactly from the area of a polygon, which is really cool. Okay. Now, the last thing we're going to introduce in this lesson is the idea of an annulus. An annulus is like a donut, okay? An annulus is how much space is left over after we remove a section from within. And the way we find the area of an annulus is we find the area of our big outer boundary and subtract the area of our smaller inner boundary. Great. So, what does that look like? Well, to give you an example, let's use this idea of an annulus to find some unknown information. And you'll notice here, it works out pretty nicely. Again, if I notice that my shaded area forms an annulus, it's a donut, it's a space with another space cut out, I can say the area of the annulus has to be the area of the big boundary minus the area of the small boundary. Well, what do I know about these particular things? One, I was told what the shaded annulus's area is. This is 2 pi units. Okay, that's helpful. What else do I know? Well, I actually know the area of the big figure as well, because I know the radius of the big figure. And the big figure is a circle. And I know that the area of a circle, ooh, let's try again, LabTad. I am so bad at drawing circles. Perfect, thanks for cheating for me. Little application. So the area of a circle is pi times the radius squared. Well, my radius is 8. So the circle is 64 pi. right? And maybe I'll write that out a little more explicitly as pi times 8 squared. And I'm asked to then find the area of the small radius. Well, I don't know what the small radius is, but I know that the area of the small that we cut out came from the formula pi r squared. I then look at the equation I have, and notice I can solve it because there's only one unknown. It's the radius squared. I start simplifying things. 2 pi is 64 pi minus pi r squared. Subtract off 64 pi. At this point, I end up getting negative 62 pi is negative pi r squared, which means my radius squared is 62, which means my radius is square root of 62. So again, this is a more involved problem because I wasn't just asked to find an annulus by finding a big area and subtracting it from a small. I was supposed to use my mastery of the idea of an annulus to find some unknown information. But once I set up my equations and solved, I was good to go. Now, as a summary of this week, it might be good to pause the video here for just a moment and see if you can write down what formulas you have memorized before we talk through them, because these ones are all going to be essential moving forward. If you paused, I'll kind of work through now. The area of a rectangle is base times height. A square is a rectangle where the base and the height are the same, so it's the base squared. A triangle is half of a rectangle, so 1/2 base times height. A parallelogram is just like a rectangle where we might have to use our triangle tools to find the actual height, but it's still base times height. A rhombus is also a parallelogram, so it's base times height, or it's also like a kite. We can also think about the size of the box that surrounds it, and it will be half the product of the diagonals, which are the dimensions of the box. Same for the kite. The trapezoid was our average base times our height, again, just like the parallelogram. The circle is pi r squared. The polygon is the area of the triangle times how many triangles you have. And the annulus is the area of your big boundary minus the area of your small boundary or boundaries. And that right there, folks, is the conclusion to our first week of Continuing Ed. Thanks so much.